We're talking about mole formula units, molecular units. So, how much does one formula unit of ammonium nitrate weigh? And so here, we'll never call this a molecular formula or molecular unit. This would just be called the formula unit because it doesn't form molecules. And so how much does one formula unit of ammonium nitrate weigh? So let's talk about what one formula unit of ammonium contains, ammonium nitrate. So in one formula unit of ammonium nitrate, how many nitrogens are there? Two nitrogens. How much does the nitrogen weigh? Well, nitrogen weighs 14.01 U average, so this is going to give me 28.02 U. How many hydrogens? Four hydrogens. Now I have a choice. I can use 101 or 108. Or I can get more sig figs. There are a lot more sig figs. But for these kind of calculations, typically we just need two decimal places. Here, if I do two decimal places, then I'm going to retain 4 sig figs. So I'm just going to do 4 times 101 U. This is going to give me 4 over 4 U. And then how many oxygens? 3. And that's going to be 3 times 16.00 U, which is going to give me, what is that, 48.00 U. And then we just add it up. When I add it up, I'm going to get 6, 0, 12, 70.06 U total. So one formula unit was going to weigh 70.06 atomic mass units. Ammonium nitrate. Ammonium nitrate has a reputation of being explosive. Ammonium nitrate. This is Oklahoma City. It's a huge explosion. Damage to the building. Ammonium nitrate is a very dangerous chemical. When you look at it, does it look dangerous to you? No. When I look at it, it looks dangerous. It's like this. There's a household rule. Never mix ammonia with bleach. Have you heard that? There have been a lot of explosions in the sink. People dumping ammonia and bleach. So if I have ammonia cleaner, I don't want to mix it with bleach. To me, that sounds very dangerous. Does that sound dangerous to you? It's going to make different gases. Could be some chlorine in there, but you can get an explosion happening with that. So you know why I think of these things as being very dangerous?
You tried this?
No. One way is you could just memorize it, but there are too many of them to memorize. Too many dangerous combinations. And so a quick way of determining it is this. So for example, if you take something like, what metal loses its electrons the easiest, you say? Did I make a mistake? Yeah. Oh yeah, you're right, 80.06, thanks. I mean, aluminum's fine. This is aluminum here. It loses electrons easiest, but it's not easily, but it's not the easiest. Things that lose electrons are a lot easier than aluminum. These metals, aluminum is pretty stable. Well, it's got an oxide coating here, but you don't have to worry about it catching on fire. What metal do you have to worry about catching on fire? Lithium. But there's things that are even worse than lithium. What's worse than lithium?
Platinum could catch on fire.
Platinum is really hard to catch on. I wouldn't expect platinum to be catching on fire anytime soon. Platinum and gold, I wouldn't use that. Well, one, it's too expensive, and two, it's not really going to catch on fire easily. Cesium. So cesium should react most violently. And so you could have rubidium and cesium together, right? I wouldn't expect anything bad. If you have rubidium and cesium, those are what we call compatible chemicals. But if you take cesium and mix it with fluorine, those would be incompatible. Because if you have cesium and fluorine, you're going to get an explosion. Why? Because cesium loses electrons easily and fluorine takes them easily. And so you're going to have a violent reaction. So cesium and fluorine are incompatible, but cesium and rubidium are compatible. Fluorine and chlorine would be compatible. I wouldn't expect any violent reaction between fluorine and chlorine because they both want to kind of do the same thing.
Also, the bleach ammonia example is because one wants to take more electrons than the other.
Yeah. So if you look at bleach and ammonia, what's the formula for bleach? Bleach is called sodium hypochlorite. And so what's the formula for sodium hypochlorite? Well, first off, what is a sodium ion? Na charge? Plus. What's hypochlorite? ClO charge? Minus. And so bleach is sodium hypochlorite. Now, when we look at the formulas, one of the first things we do is we look at the oxidation states. And so let's take a look at the oxidation states here. The oxidation state of sodium is easy because that's its charge. It's just +1. Now, for the oxidation states, I usually like to write these here. And then oxygen, what does it like to be, oxygen? -2. If you have oxygen versus chlorine, oxygen is going to win because chlorine likes to be what? Chlorine likes to be -1, but can it be -1? I'd like to put -1 here, but it doesn't add up because it's got to add up to 0. And so if I have +1, -1, that gives me 0, and then -2, but this sodium hypochlorite is neutral. So there's got to be a loser. Well, sodium is already lost. Can it lose more? Sodium has lost 1. Can it lose more? No, it can't. And therefore, who has to lose? Chlorine. But does chlorine want to lose? No, chlorine does not want to lose. Chlorine wants to gain, but in this case, it has to lose. And so chlorine's got to be what? In order to add up to 0, it's got to be +1. Is chlorine going to be happy losing? No, chlorine's not going to be happy losing. Chlorine's very unhappy losing. And so this is why bleach kills everything, right? Including humans, I guess. If you drink bleach, you don't want to drink bleach, right? There's somebody saying that. Somebody was saying that, oh yeah, to kill the coronavirus, you drink bleach, right? But that's got to be, no sensible. I mean, it's got to be one of those fake quotes. I can't believe anybody would say that. Maybe gargle with bleach. Yeah, you could gargle with bleach, or you could. We used to have bleach tablets. I told you we carried bleach tablets to kill the. So I've had to drink water containing bleach. It almost made it not worth it, But when you look at the water, this was backpacking in Ventura. Backpacking is very dry, and so sometimes you'll get a creek, and the creek is just nasty because it's just a stagnant pool of water, right? And at the time, they didn't have these water filters that can filter out everything. So you just get this water out of this cesspool, and then you put the bleach tablets in there and you shake it up. So it almost made it not worth it, going there, having to drink bleach water. Fortunately, I didn't die, but everything depends on how concentrated it is.
Also, you would need like super concentrated version of it or enough of it in order for it to have any.
Yeah. Well, they use bleach. When I was in the lab, we used bleach for everything. I used to like the hydrogen sulfide. I told you about this hydrogen sulfide. One of the characteristics of that is the smell. What does it smell like?
Rotten eggs.
Rotten egg. So I used to work with hydrogen sulfide a lot. The smell is just awful. And so to kill the smell, do you know what I used? I used bleach. And then what bleach did was hydrogen sulfide is like this. And hydrogen is +1, and sulfur is what? Its preferred charge, -2. And so what I did was I oxidized the heck out of it using bleach, lots of bleach. And then you know what that converts it to? If you oxidize the heck out of it and you just max it out, do you know what it converts it to? In water, it converted it to sulfate. Sulfate doesn't have any odor. And so what you do is just, depends on how much you oxidize it. And so bleach is called an oxidizing agent. Oxidizer. So I think that story about the bleach, they were talking about maybe gargling with an oxidizer like bleach or maybe something less harsh, like iodine. It should be a lot less harsh. Because the virus, the coronavirus is upper respiratory tract, your throat, and your nose. People, one of the early symptoms is runny nose. So this is why you want to kill it there, not in your stomach. And so this kills off the odor, which is quite nice. And so bleach is an oxidizer. Why is bleach an oxidizer? Because chlorine is what we call electron poor. Chlorine would love to be not +1. Chlorine would love to be -1. And so this is what we call electron poor. Electron poor species are oxidizers. Well, things like viruses and bacteria, like E. coli, whatever, those are, you can burn. Can you burn bacteria? You can burn. Those are fields, those are what we call electron rich. And so the bleach is just going to take the electrons from those and kill off all those species. However, ammonia, let's take a look at ammonia next. If we look at ammonia, which is NH3, which one do we do first? Well, there's actually some rules. I showed you the rules in the supplement, right, for oxidation numbers, oxidation states. Remember that? Or did I show you that? Pretty sure I showed that. We also have rules here in our book, but they're much later. They're in maybe here. Chapter 19. Chapter 19, section 19.3, oxidation numbers. So you may jump ahead, section 19.3 there, and take a look. Now, when we're doing these numbers here, and then there's a set of rules here that we're going to use to help us. These rules are going to be very similar. Not all of them are the same. Different books will have different wording of the rules. I have a much simpler set of rules. My set of rules is very short. The oxidation number of each atom in any elemental substance is 0. This is a very useful drill. The oxidation number of a monatomic ion is the same as the charge on the ion. So I have a monatomic ion here, sodium. The oxidation number is the same as the charge, which is +1. The oxidation number of combined oxygen is -2. Oxygen is the oxidizer, right? That's the whole term oxidizer comes from oxygen. Oxygen is one of the best oxidizers. And so it likes to take the number of electrons it wants, which is 2. And so usually we assign oxygen 2 because it's a great oxidizer. Sometimes we can't, though. There's other things interfere with it. So in this case, sometimes we get peroxides, where it comes out to -1. Sometimes we get superoxides, where the average is -1/2. Somebody asked me about that yesterday. Yeah. Sometimes the oxygen loses, like in OF2. Somebody more powerful comes. Who can be more powerful than oxygen? Actually, a lot. A lot of things can be more powerful. And what would be more powerful on the periodic table than oxygen? Fluorine. Fluorine's the most powerful on the periodic table. So if it comes down to oxygen versus fluorine, who's going to win? Fluorine. Fluorine only wants 1. And so it takes 1. And so we have this. This is called oxygen difluoride. This is not called difluoromonoxide. And there are 2 ways we could have named this. We could have named this difluoromonoxide. If we call it difluoromonoxide, that means oxygen 1. If we call this oxygen difluoride, that means fluorine 1. Fluorine's going to win. And so that means oxygen comes out to +2. Is oxygen going to be happy? No, oxygen is not going to be happy. Is OF2 going to be very stable? No, it's not going to be very stable because it's unhappy. The same thing with bleach. Bleach is not so happy because, why? Chlorine. Even chlorine in the 0 is unhappy. Even chlorine in the 0 is unhappy. Because do you want to inhale this stuff? This green gas, chlorine? You don't want to inhale it because it's unhappy. It wants what? It wants 1 electron. In fact, you'd use chlorine to kill bacteria, viruses, whatever. Well, this is certainly not going to be happy because this is even worse, right, than this. So bleach. I have a friend that works for the Army in Maryland, and he's a biochemist, PhD biochemist. And you know what he works on? He works on nerve gases. Yeah, he's not trying to develop a better nerve gas. Are you familiar with those nerve gases? Like you get a drop of nerve gas agent on you and you end up dying. Something like that. So I asked him, because it's just like you work with this dangerous stuff that could kill you. And so if you have a little accident, then you could end up dying from making a mistake. So you got to be extra careful. So I asked him, how do you get rid of it? If you have some like nerve agent, how can you disable it? That is what you do. So if there's nerve agent, like they do things like they spray it on leaves. People walk by. This is one of the things. It's like so they spray it all over the leaves, and then you have people walking by, and they get some on their arm. They die. And so how they, what they do? Bleach. Bleach kills. And so he said, well, if you just bleach it, you can disable it. And so if there's any nerve, like in Tokyo, the subway, there's some nerve agent there, just bleach it out. Or kill it. There's some kind of terrorist thing there. And so if there's any kind of thing, well, maybe you want to focus on bleaching pretty much. Yeah, bleach kills a lot of things. Bleach is a very useful chemical. And bleach, this is pretty much, when you put chlorine in water, you make bleach, basically. That's chlorine in water. Well, it kills a lot of things because it's a great oxidizer. And a lot of living things you can burn. Another way you can do is just burn it. Burn all the leaves, and that will get rid of the nerve agent on there because the nerve agent will burn. And the things that burn are electron rich, they're fuels. And so something like ammonia is, well, let's take a look at the oxidation states here. So we'll continue on here. The oxidation number of combined hydrogen is +1. Sometimes it's -1. And so what we'll do is we'll sign hydrogen here +1. And that, if hydrogen is +1, that makes nitrogen what? -3. Well, -3 is its preferred charge. That's good. Nitrogen's happy at -3. Uh-huh.
So you talk about reach taking electrons and oxidizing. Is that the same when you have like a stain?
Yeah, right. Because a lot of those stains are like plant pigments. Not all of them. Some of these colors are like from insects. You know, like I don't know. I haven't looked into it, but some people don't want to eat like red food color because red food color is made from extract of some insect, and they don't want to eat any insect, so they don't want to eat that red food color. Have you heard that? Yeah. But a lot of them are just plant pigments. A lot of these colors, and those plant pigments, you can burn it. You know, if you burn the plant, is it going to be pigmented anymore? No. And so a lot of those pigments are what we call organic, and these organic things are things that could be used as fuels. And if you have an oxidizer, then you can have a, we call it a reaction. So these numbers, they require some interpretation because it's not simple interpreting numbers sometimes. Oxygen is very happy at -2. And so we call this, we don't call this electron rich here. But nitrogen, you would think nitrogen should be very happy at -3, shouldn't it? Because that's how many electrons it wants. But it's like if you have too much, you know, that's like 3, nitrogen has to hold on to it. How many protons does nitrogen have? Nitrogen has 7 protons. 7 protons gives it a +7 charge. And then it has 10 electrons. So you got 7 protons with 10 electrons. It's hard to hold on to that many electrons, right? The more protons you have, the more you can hold on to the electrons because electrons are negative. And so oxygen has no problem holding on. It has 2 extra electrons, it can hold on to it. But nitrogen's got a whole bunch of extra electrons, it's harder to hold on to because you've got too many. So somebody can come along and steal some electrons from nitrogen. It's a lot easier. And so for nitrogen, a -2 charge on oxygen, we consider good, stable. A -3 charge, we start to think of it, it's a little bit rich in electrons. And so some thief can come along and steal some electrons. And what that thief is going to be is an oxidizer, right? And so here, this would be considered kind of electron rich. A +1 on hydrogen is fine. So electron rich means it's a fuel, a potential fuel. Whereas versus water, a fuel you can burn. Could we burn water? Yes, but it'd be very, very difficult. Water is not considered a very good fuel. It's not considered a very good fuel because oxygen holds on to these 2 electrons very tightly. So oxygen holds on to those 2 electrons very tightly. It's not going to lose them. We need an oxidizer. You know, when you have combustion, we need 2 things. We need a fuel, methane, and an oxidizer, oxygen. And then we'll have a combustion reaction. So here we have a fuel. In this case, the fuel is ammonia. Methane is a great fuel, by the way. You know, what makes methane such a great fuel? Let's look at the oxidation states on methane. What are the oxidation states on methane? So what we do is we do hydrogen at +1. If hydrogen is at +1, what does that make carbon? Carbon must be, now this is +1 times 4. So the hydrogen is plus, 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 and plus. This gives us a total of +4. And that means carbon must be -4. We showed this is just individual. Each hydrogen is +1, and we got 4 of them. This is the total charge. So if carbon has 4 electrons, is it going to hold on to those super tight? That's a lot of, no, it's a lot of electrons. So if an oxidizer comes along, sees all those electrons, it's going to think this is really rich, you know? This is like if a thief comes along and sees this person has a lot of gold and they're not holding on to the gold very tightly, they're going to take the gold. And so an oxidizer comes along like oxygen and takes it. You know, how many, in the end, how many electrons does carbon have? Well, carbon gets completely stripped of all of its electrons. Right, so a thief comes along like oxygen, takes all the electrons, and then carbon ends up as CO2. How many electrons does it have now? Well, oxygen likes to be -2. So what we do is, this is just for one oxygen, or we can bookkeep. We have 2 oxygens, both at -2. This is going to give us -4. That means carbon must be plus 4. So carbon is plus 4. So we went from being extremely rich, -4, to being not just even. Even would be 0, and that's plus 4. So altogether, it lost a total of 8 electrons. So it was rich, it had 4 extra, let's say gold coins. But now, not only did it lose those 4, it lost another 4, and now it's completely broke. Right? Now it's completely broke. And so methane's a good fuel. Here. Ammonia is also a fuel. You know, you can burn ammonia. It's not going to burn as nicely. And this CO2 is not going to, I mean, it's not going to kill you so much. I was listening to this thing this morning about, you know, in California, you have a choice. You can purchase like green electricity versus brown electricity. Are you familiar with that? And so I noticed if you don't opt out, you're getting the green electricity, which I didn't opt out of that. So I'm purchasing green electricity, but you know the way the accounting is, you know, and you think, okay, that's good and environmentally, you know, conscious, but you know, then you have these businesses that are not all business. There are plenty of great businesses, of course, but you have some that are, you know, the way they and they're loose with how you can label, you know, green versus brown. You know? And so you might be thinking you're purchasing green, but you're getting brown energy because they can label things in certain ways. Some more investigation needs to be gotten into, but it turns out it's very profitable for certain companies, you know, because they can manipulate the system. So anyway, they have certain criteria for green energy. How many pounds of CO2 you generate? This is not balanced. We'd balance it later. But this is just looking at this as a reaction. So whenever we mix electron-rich species with electron-poor species, you're going to have a reaction. And that reaction could be quite violent, depending on how rich or how poor these things are. So when you mix ammonia with bleach, that's a bad combination. You got one person who has lots of gold coins, the other person has nothing, then there's going to be a redistribution of gold coins. So keep these apart. Don't mix them. And then you can form toxic gases like chlorine, or you know, chlorine and oxygen, like chlorine monoxide, chlorine dioxide, those types of things can be poisonous gases. So we keep them apart, but take a look at this one. Ammonium nitrate. Look at the oxidation states on ammonium nitrate. First, let's do ammonium. Hydrogen is what? In compounds, rule number 4, hydrogen is +1. And then these have to add up to +1. So I have 4 times +1 gives me +4. +4 plus what gives me +1? +4 plus a -3 gives me +1. So when we look at that, nitrogen at -3 is what we call electron rich or electron poor? Rich. That's pretty rich. It's got the gold coins. It's hard to hold on to. Nitrate, which one do we do first? Rule 3, oxygen. It gets -2. My rule is different. My rule is this. The element furthest to the right gets its preferred number of electrons rather than this. And so I have a much shorter one. Okay, so we have 3 of them. I don't call oxygen electron rich. This is what you need to learn. You know, oxygen is happy as is. It's very stable because ammonia we can burn. Can we burn water? Would you call this oxygen electron rich? Have you ever tried to ignite water? No, we use water to put out fires, fuel the fires. And so water is not a good fuel. It is possible to burn it, but you'd have to have a very powerful oxidizer to do it. And that's it. And so oxygen's happy as is. I wouldn't call that rich. Over here, this is rich. Electron rich. What about nitrogen? What's nitrogen here? +5. So you have this nitrogen, which is at +5, and you have this nitrogen, which is -3. Is that what would you say? An equitable situation? One nitrogen has +5, the other nitrogen has -3. So this nitrogen's going, boy, that's pretty rich. This nitrogen's really rich or poor? Really poor. And so this nitrogen is called electron poor. The oxygen's happy as is, the hydrogen's happy as is because, water's happy. Water is very stable, and the planet contains lots of water, which is good for life. So we have this electron poor, electron rich situation. That's fine if the 2 nitrogens don't come into contact with one another. And so we can put them together like this. But the situation will rapidly change if the 2 nitrogens come into contact with one another. And so this is what we call metastable compound. It's somewhat stable, but it's not really stable. And so you could buy ammonium nitrate. I mean, it's fertilizer, basically. Fertilizer, you need lots of nitrogen to put in the soil. So you could use ammonium nitrate fertilizer for that. But it's kind of stable, but it's not really stable. You have to be careful how you handle it. So for example, you don't want to get it too hot, because if you get it too hot, what's going to happen? Heat will increase the kinetic energy. And so if you start getting this vibrating, if you start getting these vibrating a lot, then they can slam into one another and react. And so you don't want to get this hot. This is metastable. Don't get it hot. In fact, you might want to keep it in the refrigerator. If you keep it in the refrigerator, they don't vibrate that much. It'll be more stable. And so don't heat it up. I think what they did was they put even more fuel in there. Ammonium is not the greatest fuel. Ammonium and ammonia, these aren't the greatest fuel. In Oklahoma City, he put even more fuel in that mix. I think hydrocarbons, other fuels. More fuels that are not methane, but methane-like. So ammonium nitrate was one component. The other component was fuel, a better fuel. Ammonium nitrate alone is enough. Did you see the explosions in China? I forgot the name of that. Let's see. You haven't seen that? This is just straight ammonium nitrate. This is no fuel in addition to it. Uncensored version, but the uncensored version has foul language. Well, maybe we'll just watch this.
Vote yes on PCC. Pasadena City College provides high-quality, local, affordable education. How big are you? What the? Whoa! With your belt.
Yeah, it just,
Yeah, go
oh, it's a little hot. Oh, now they're going. Give it the truth.
Yeah. Yeah, that was ammonium nitrate.
So what happened? Like how much ammonium nitrate?
Tons of ammonium nitrate.
What exactly happened?
Well, something got it ignited, or there's some acid or something. They're thinking there's an investigation there, but it's pretty much everything was vaporized there. There was a long investigation. It turned out to be ammonium nitrate being stored in a warehouse, and there were tons of it. So that was just a huge explosion. Then, are you familiar with Texas City? Anyway, the computer just crashed. That happened in China. I think some people died in that one. 173
In that explosion?
That explosion. But in Texas City, a lot more people died. You know how many people died in Texas City? I think it was 600 people, including like school children. So that was mostly industrial workers there. What's that? So Texas. Well, there's a video on it. I'll show you sometime later. But that was ammonium nitrate also. And so you're taking something that's rich and poor. These are two incompatible things, and they're in the same compound. So this is quite dangerous. And so this is one of the things we do. One of the things we do to try to understand properties is to do the oxidation states here. And so even though oxidation states are discussed in chapter 19, we're doing it early so that we can get a little bit more insight. Otherwise, the other way you can do it is just memorize them, but there are too many incompatible things, like I said before, it's too much to memorize. All right, I guess this is rebooting, so it's going to take some time. All right, so next is section 7.3, which deals with the mole concept. So let's talk about that. So we could have like 1 unit, or 12 units. If we have 1 unit, then it's just 1 unit. If we have 12 units, then we have a name. We call that a dozen units. If we have 6.022 ... because there are more digits here, 6.022 times 10 to the 23rd, we call that a mole of units. And so these are counting numbers. And so mole is a counting number. So if I had 2 moles worth of CO2, 1 mole of CO2 is about this much, gas. 2 moles of CO2 would be twice as big. 3 moles of CO2, 3 times. So 1 mole of CO2 is about 25 liters. 2 moles of CO2 is about 50 liters. 3 moles would be 75 liters, etc. The problem is do you know the origin of the dozen? Because when you look, did somebody have 12 fingers? At one point in history, is that why we got the most famous baker maybe had 12 fingers and so it was counted.
So it gets.
Okay, yeah, maybe that's true, but do you know? I'm just guessing. You're right. That is a total guess. I don't know. Do you care? Well, I often wondered why. Why the odd number? Because
It says here, notice that the atomic mass and the molar mass of carbon-12 are numerically equal.
Yeah. So we might not know the origin of the dozen. I don't know. And I never cared enough to go look it up. But you need to know the origin of this number. Where does this number come from? And why didn't they pick an easy number like 1 times 10 to the 23rd? If they did 1, or maybe make it even easier, 1 times 10 to the 20th. If you had 1 times 10 to the 20th, CO2 would still be about the same, a little less, But something like that. 1 times 10 to the 20th would be easier to remember, at least, than this number. Because this is only to 4 sig figs. Your book only does it to 3 sig figs. Your book goes 6.02. But we like to do things to 4 sig figs. And so that's why I did 6.022. If you need more than 4, you can look it up. And so we need to know the definition of the mole. And that's going to tell us where it comes from. And we already know the definition of the U. And so the origin of the number is really weird. 1 mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. So there's a tie-in with the AMU. Remember, the AMU is defined as 12 AMU is exactly the mass of a carbon-12. Why is it defined this way? So it turns out that there are approximately 6.022 times 10 to the 23rd carbon-12 atoms in 12 grams of carbon-12. Therefore, 1 mole of anything is equal to 6.022 times 10 to the 23rd of anything. So 1 mole of units is equal to 6.022 times 10 to the 23rd units. So to make a long story short, this is why they did this. How much does a carbon-12 atom weigh? One single carbon-12 atom. One single carbon-12 atom weighs exactly 12 AMU. And so this is called isotopic mass or atomic mass. And so we have 12 U per carbon-12 atom or nuclid. Nuclid's another way I can say it. If I had 1 mole of carbon-12, how many carbon-12 units do I have? I'm going to have 6.022 times 10 to the 23rd, carbon-12 atoms. And how much does that weigh? That weighs 12 grams. Exactly. And so this says I'll have 12 grams of carbon-12 in 1 mole of carbon-12. Do you know the mole has an abbreviation? You know what the abbreviation for mole is? MOL. But you think that abbreviation doesn't really save us much. We just got rid of the E. It's not much of an abbreviation, is it? But that's the abbreviation. This is what we're going to use here. And so, you know what this means? I memorized this. What does the average carbon atom weigh? 12.01 U per carbon atom. This is the average one, not carbon-12, per 1 average carbon atom. So I have 12.01 U's. Or, if I had a mole of them, it would weigh 12.01 grams of carbon atoms in 1 mole of carbon atoms. So, the reason why this definition has such a weird number is so that the two numerical parts of this are the same. So if I had a single carbon, it'd be this in U. If I had a mole, it'd be the same number except in grams. If I have a CO2 molecule, a CO2 molecule weighs 44.01 U. That's for 1 CO2 molecule. And so if I had an average carbon dioxide molecule, it was 44.01 U. But if I had a mole of average carbon dioxide molecules, it would weigh 44.01 grams per mole of CO2. So if I take that mole of CO2, which is about 25 liters, if I take 25 liters of CO2, it's going to weigh 44 grams. And so this is why the mole is a strange number. It's because we have this relationship between this, which we call molecular mass, and this, which we call molar mass. This is also called formula mass. If it doesn't form molecules, we call it formula mass. If it forms molecules, we call it molecular mass. But we're going to have this relationship between these two here. Molar mass is for anything, whether it's for molecules or formula units. So we can do some calculations here. Let's see what calculation we're going to do. Let's say I had 1 billion H2O molecules. How many grams of water is that? So 1 billion would be 1 times 10 to the 9 H2O molecules. And there are different ways I could do this. But I need to get rid of H2O molecules, and one way I could do that is I could use the mole concept. This number, 6.022 times 10 to the 23rd, has a name. And so 6.022 times 10 to the 23rd H2O molecules would be called 1 mole of H2O molecules. Or the name for this number is called Avogadro's number. So if I had an Avogadro's numbers worth of water molecules, it would be 1 mole. So I need a lot of water molecules to make a mole. I only have 1 billion. And so this, if I stop here, I'll have the number of moles of water molecules. But the number of moles of water molecules is a little abstract. And so what I'm going to do is I'm going to try to figure out how many grams in it. And so H2O consists of 2 hydrogens. Each hydrogen weighs 1.01 U. But what I'm going to do now is I'm going to just say I have 2 hydrogens, it weighs 1.01. And I'm not going to put units there. I don't put units there because there are 2 ways I can read this. This is 1.01 U per hydrogen atom, or 1.01 grams per mole of hydrogen atoms. So I'm going to call this, if I had 2 moles, like if it's 2 dozen, this is going to give me 2.02. And then oxygen is 16.00. So if I have 1 oxygen, it's 16.00. And that's going to give me the average mass of the water, which is going to be 18.02. Now this 18.02 we have two choices. We could call it 18.02 U per molecule of water. Or we could call it 18.02 grams per mole of H2O molecules. And a molecule and a mole are two different things. A mole is just a number. A molecule is usually individual. A lot of people get it mixed up because they look similar. And so if I have the number of moles of H2O molecules, then I can say that a mole of water on average weighs 18.02 grams of H2O per mole of H2O molecules. And so the H2O molecules cancel out. The mole of H2O molecules cancel out, and that leaves me with grams of H2O. So how many grams is a billion water molecules? How much does that weigh in grams? So I'll say 1 times 10 to the 9th divided by 6.022 times 10 to the 23rd times 18.02. This is going to come out to 3 times 10 to the negative 14 grams. I would know, let's see, 10 to the minus 14, I don't know what that is. 10 to the minus 12, I do. Do you know what 10 to the minus 12 is? Metric prefixes? Let's see. 10 to the minus 12 is, yeah, pico. And so this would be 10 to the minus 12, that would be, I make this smaller, so I got to make this bigger. So this would be 300 times 10 to the minus 12 grams. And so this would be 300 picograms of water. $300 picograms of water. Do you think that's visible to the naked eye? Maybe not. You know, they say a dollar bill. They say a dollar bill weighs about a gram. So if you chop up the dollar bill into a million pieces, each of those individual pieces would be 1 microgram. So if you take that dollar bill and chop it up into a billion pieces, then that individual piece would be a nanogram. And in order to get a picogram, you'd have to take that dollar bill and chop it up into 1 trillion pieces. If you chop it up into 1 trillion pieces, that would be equivalent to a picogram, I think. Is that right?
In the book, it says you could verify your answer to see if it makes sense. I didn't understand how they were rounding things. It's like, let's say if this is a 0.035 moles of H2O, they would round it accordingly, and sometimes they just do it by whole numbers.
Yeah, the book is overzealous in terms of rounding. They don't really care so much about round like that. We usually round things at the end. I carry extra digits and round the final answer. I don't.
Yeah, so like they might round the H2O to 20 instead of 18.
No, that's not good. Some people on tests are overzealous about rounding. I don't know why. 20 grams of water per mole. That's only 1/16.
But this is when they're verifying to make sure that it matches with the.
Oh, okay.
That's,
All right.
That's what they're doing, and I don't understand that, like why they're rounding so much.
They're rounding so much to, they want to just verify order of magnitude. And what they're doing is they're just checking, is that a reasonable number, 10 to the minus 14? So what they do is they go like this, 10 to the 9 divided by 10 to the 23. So you bring this up and you subtract it. And so what we get is 14, 10 to the negative 14 here. Times about 10. Which should give us about 10 to the negative 13 ballpark. But then you look at the coefficients. And so this is what they're doing. They're looking, 20 divided by 6 is around what? 20 divided by 6, so you could just do 18. 18 divided by 6 is about 3. So they're just looking, does that make sense? They're trying to catch gross errors. Let's say instead of this coefficient, I got 8. And so they're saying, well, if you do 20 divided by 6, it's not going to be 8. Or 18 divided by 6 is not going to be 8. And so they're just trying to just do rough calculations to see if it comes out close. This is a way to double check your calculation without repunching it in the calculator. Just to see if you're in the ballpark, correct region. So what they're trying to do is they're trying to catch gross errors from accidentally flipping these. Sometimes people don't divide, they multiply, so they accidentally multiplied this. If they accidentally multiply this, we get 6 times 18, or 6 times 20. 6 times 18 is more difficult than saying 6 times 20. 6 times 20 is going to be about 120. And so we get a coefficient around 120 rather than a coefficient of 3.
Okay.
And so they're just kind of ballparking this to see if we
Do you recommend doing that when we're doing it? Or is it?
Sometimes, yes. But most of the time, I recommend that people just rekey it in the calculator. People are always doing that. If you're doing a calculation, then they're thinking, they don't have a calculator, and so they're trying to do it in their head. When you try to do it in your head, then you can round the number quite a lot. And so if I were doing this in my head, I might, rather than call that 6, I might call that 10. And rather than calling it 10, well, I can call it 10 here. So I do 10, I get 10 to the 9 divided by 10 to the 23 gives me 10 to the minus 14. And then I get 20 divided by 10, which gives me 2. So I'll get about 2 times 10 to the minus 14. 2 times 10 to the minus 14 is ballpark. And we got 3 times 10 to the minus 14, so that's close enough. So we're on the right track. However, it's meant to catch gross errors, not minor errors. Gross errors. So we could do that. All right. Does that?
That answered, yeah.
Okay. But there's something that's commonly done. So there are lots of calculations like this. All the calculations involve dimensional analysis. And so we'll take a look at some of these calculations, but we'll take a break first, and then we'll look at the calculations after the break.